Next couple units, we're going to look at a couple of types of functions that are often used in many areas, business being one of them, but also other areas as well. So basically what we're going to do with each one is I'm going to show you the graph of them, and then of course how we can transform them, because you guys know how to transform graphs by flipping and stretching and shifting. And then we'll talk about equations involving these types of functions and specific situations where we can use them. So the first one we're going to talk about is something called exponential functions. And an exponential function simply is, it's a function where you've got a power, but there's a variable in the exponent. Okay. Xavier? So you guys have been graphing some functions that have powers, but the exponent has always been a number. So like if you graph this, you're going to get a parabola. If you graph this, or if you graph this, you're going to get different shapes that we've seen early on in the year. Okay? But this time, what happens if the variable is actually in the exponent? Okay? So that's called an exponential function, and we refer to the base of the power as c, okay? And it's going to be larger than 0. And x is the exponent, and it's a variable. So what do these functions look like? Well, it's best just to start with some basic functions, use a table of values, and from there we can get an idea of what they look like. So here's a couple of examples where we've used 2 as the base, x as the exponent, and then 3 as the base and x as the exponent. So usually we pick our x's around 0. So I'm going to go -2, -1, 0, 1, and 2. So the first one, I plug -2 in. You remember how to evaluate a negative exponent? That's where we have to change it to a positive exponent by flipping the base. So this is the same, 2 over 1 becomes 1 over 2, flip the base, and then you can make that positive. And that is equal to 1 over 4. Two to the -1, again, to make it a positive exponent so you can evaluate it, flip the base from 2 to 1/2 and raise it to the first power, and we get 1/2. 1/2 to the 1 is 1/2. These ones we should be able to do. 2 to the 0. Anything to the 0 power is 1. 2 to the first. Don't overthink. 2. 2 to the second. 4. So that should give us a pretty good idea of what it looks like. So -2 1/4 is pretty close to the x-axis. -1 1/2, it's a little bit higher. 0 1, 1 2, and 2 4. So you can see the shape that it takes. Okay, it's going to be a curve that looks like this. Now notice how I've drawn the left side of the curve, and I'm going to talk about this in a second. It doesn't pass through the x-axis. And I'll explain why that is. If you think, like, if you go 2 to the -3rd, it's 1 over 2 cubed, which is 1/8. If you go 2 to the negative fourth, it's 1 over 2 to the fourth, which is 1/16. That fraction keeps getting smaller and smaller and smaller and smaller, but it's never going to hit 0. Okay? That's why we sort of draw the curve along the x-axis, because it's never, y is never going to work out to 0. It's going to be a really small fraction the more I go into the negatives. So similarly, if we did 3 to the x, we'd get much the same thing. So I'm going to use the same values for x. 3 to the negative second is the same as 1 over 3 to the positive second, which is 1/9. 3 to the negative first is the same as 1 over 3 to the positive first, which is 1/3. 3 to the 0 is 1. 3 to the 1 is 3, and 3 to the second is 9. So this time we get 1/9. We're even closer to the x-axis. Get 1/3. Get the same point at 0 as we did for 2 to the x. But then it starts to climb higher more quickly. And 2, 4, 6, 8, 9. So it's still a curved shape, but it's slightly different. Notice that the bigger the power, if you look at the right-hand side of the graph, it climbs quicker. And if you look at the left-hand side, it kind of dives quicker, but then goes along 0. Okay? So, some properties. If we look at these two graphs, what's the same point that both of them pass through? 0, 1. And that's going to be the case for every one of them. Doesn't matter what the base is. Could be 4, 5, 6, could be fractions. 1/2, 1/3. They'll always pass through 0, 1. Because whenever you plug 0 in as the exponent, the answer is always 1. There's no x-intercept, okay? Because like I told you, we keep getting closer and closer to x the more we go down the negatives, but we never hit 0. So we never go through the x-axis, which means there's no x-intercept. The domain for these things is going to be everything, because it goes to the left forever and to the right forever. And the range, the lowest is 0, but not including, because it never hits 0. And it goes up forever, so it's 0 to infinity. But notice I put a parenthesis around the 0, not a bracket, because we don't include 0. So how do we address that not including 0? Well, what we need to do is we need to put an imaginary line, dashed line, showing on the left-hand side the graphs get close to that dashed line but never touch it. And what do we call a line that some curve approaches but never touches? We've seen it before. We talked about it briefly. We call it an asymptote. And asymptotes, well, they can be vertical, they can be horizontal, they could be diagonal. This one's horizontal because it goes like this. Okay, so there exists, whoa, stop. Let's try that again. There exists, oh yeah. A horizontal asymptote on the x-axis which is the equation y equals 0. On the x-axis, every y coordinate is 0, so we call it y equals 0. Now, the behavior of the graph, finally, we saw, and we talk about what's its behavior from left to right. So as you move to the right, okay, go away. We saw that when the base was greater than 1, like 2 and 3, the graph increases. It just climbs as we move to the right. If the base is a fraction between 0 and 1, which we're going to see in a second, it actually goes down. It decreases and approaches that horizontal asymptote. Like I said, we're going to see that in a second. Okay. So, like I said, what happens if the base is a fraction? What does it look like? Well, right now, all I've told you is that as we move to the right, it decreases, but this will show you. Now, we don't have to use all 5 points in the table of values. This will be good enough to get our shape. Okay. So 4 to the negative 1 is the same as 1 over 4 to the positive 1, which is a quarter. 4 to the 0 is 1. That's always going to be a point, no matter what the base is. And 4 to the 1 is 4. So just even those 3 points, we have a pretty good idea of what it's going to look like. Climbs to the right, and then moves along the x-axis to the left, but never touches, which means, and you have to include this as part of your graph, right? That's a complete graph of 4 to the x. You need the horizontal asymptote in there to show the reader, or to show whoever's looking at it, that as you move to the left, it's never going to touch that dashed line. If we compare that one to 1/4 to the x, and we use -1, 0, and 1, well, first of all, 0, 1 is always there. Always. But this time, 1/4 to the -1, well, flip the base and change the exponent to positive. So I get 4 over 1, or 4 to the positive 1, which is 4. And then down here, 1/4 to the first power is going to be 1/4. So basically, it's flipped horizontally. At -1, it's going to be 4. Still going to be a 1 at 0. And then it's going to be 1/4. So it's going to look like this. So if we flip the base, really what we're doing is a horizontal flip. We're taking one base and then we're just flipping it over the y-axis. And again, to complete the graph of an exponential function, you need the asymptote. Okay. So you can graph them if I give you the function, or you can tell me the function if I give you the graph. So this one here is pretty stretched out. Well, it's going to be something to the x. What does it look like? We got to find points. Well, we know 0, 1. Where does it look like when x is 1? What does y look like? Yeah, it looks like 5. When x is 2, what does y look like? Way up here. It's actually 25. So what would be the base? Something to the 0 is 1. Something to the 1 is 5. Something squared is 25. What's the base? 5. That's it. Okay. So those are what the basic exponential functions look like. The next step will be talking about transformations, if there's a number in front or if there's a negative in front, if there's a number at the end, if there's a number after the x in the exponent, if there's a number before the x, all these things cause transformations. But I just want to wrap this one up by showing you one area where we actually use these things. Okay? And this would be in the area of investing. Exponential functions, also like population growth, we use it in chemistry, the growth or decay of substances, but I want to focus on a business application. Okay? So let's say you've got $4,000. You want to invest it. Okay? The amount that you invest, we always call the principal. Okay? When you invest money in a financial institution, they pay you for investing, right? Because they get to use your money for investing in other things so that they can make profits, okay? That money that they pay you works out to a percentage per year, which we call interest, okay? So if we look at this question here, if you invested for 1 year, how would you figure out how much money you make? Yeah, you just take how much you invested times it by 4%. But normally people leave their money in, if they're going to do an investment, they leave it in for more than a year. They leave it in for several years, okay? So that they get interest every year. Interest is calculated 2 ways. You can either get 4% of 4,000 every year, which works out to what, $160, I believe. So you get $160 interest every year. And so whenever you decide to stop that investment and take your money, it'll be 160 times however many years you invested. That's something we call simple interest, which is normally not used. It's used in places, but usually what happens is interest is compounded. What that means is that, let's say, don't write this down yet, because I'm going to write a chart here. To figure out how much we make after the first year, we times this by 0.04 and we add it to the original amount. So this is the original amount you invested. This is how much you get. Oh, sorry, this should be 0.04. So what's sitting in this investment after 1 year? $4,160. Okay. If it's compounded annually, at the end of the second year, they don't calculate the interest on the 4,000. They calculate the interest on how much you built after the previous year. So you're actually getting more money. So at the end of the second year, the interest, it wouldn't be 4,000 times 0.04. It would be how much you had in the investment after the first year times 0.04 added to what you have in your account after the first year. So that would be the second year. That's compounding interest. That means that we're calculating interest on previous interest. Okay? which is normally what is done for investments. So when we talk about compounded annually, we are talking about interest on interest. It's not just the 4,000, it's how much you've built up from the previous year with the previous interest. Okay? And sometimes they're not necessary, interest is not necessarily calculated once a year. With some, it might be twice a year. So it would say compounded semi-annually, which means they calculate interest twice a year, which means you're actually going to get a little bit more money. Some compound it monthly, which means every month they calculate interest, and then the next month calculate interest on that interest. The more times interest is calculated in a year, the more you're actually going to get. Right? I mean, not a huge amount more, but it's a little higher. Okay? So if you see an investment that's being compounded semi-annually or compounded monthly, that's something worth looking at. Okay? Because it's compounded annually, because we're building interest on interest, okay, the relationship between how much you invest and how much you get is actually exponential. It grows quickly. Okay? Like your investment starts, you don't have to write this, but your investment would start, you know, let's say this is $4,000 here. So after the first year, you get a little bit of money, but then it starts to climb steeper and higher. So it's going to look like that. It's not, if it was simple interest, it would just look like that. You get the same amount every year. But compound interest grows quicker. So let's see how that grows. So yes, it is exponential. And then I'm going to start a table here. So my columns, I'm going to be the end of year, because that's when interest is calculated. How much you invested, and how much you have in principal and interest. And we're going to see that there's actually a quick way that we can calculate these. So at the end of year one, you have $4,000, and interest is about to be calculated. And how is it calculated? We take 4% of 4,000, and then we add that 4,000, right, to get the total. So think that we're taking 4% and 100% of the principal. So a quick way to find the principal and the interest is don't multiply by 0.04 and then add 4,000. Just multiply by 1.04. That's going to tell you how much your principal and interest is. So when you do that, at the end of year one, you're going to have 4,160. At the end of year two, what's our interest? Well, our interest is what we calculated in year one. It's this. That's our interest. How do we calculate the new amount? Principal and interest. We take this amount and times by 1.04 again. So remember, this is how much you made after the first year. We're going to take this amount, which we know is 4160, and we're going to times it by 1.04 again. Every time you calculate new principal and interest, you multiply by 1.04. So 4,000 times 1.04 times 1.04, or 4160 times 1.04, would give you this. $4,326.40. Okay, so our money's climbing. At the end of year 3, well, what's our principal at the end of year 3? From the previous year, it was 1,000 times 1.04 times 1.04. How do we calculate the new amounts, principal and interest? We take what we had the previous year and times by 1.04 again. So this is how much we had after the second year. Then to get to the end of the third year, we got to times by 1.04 again. And this time we get $4,499.16. So we've almost made, after 3 years, $500 on our investment. Not bad. Can you see a shortcut? So I could do the fourth year without even worrying about writing this, just going straight to here. Can you see a pattern? Yeah, 4,000 times, notice how many 1.04s we multiplied by? It's the same as the year number. So for this one, all we'd have to do is go 4,000 times 1.04 to the fourth. That would get our new amount, which is a lot quicker than having to keep multiplying by 1.04 on your calculator. And you would get, in this case, 4679.43. So for year 5, again, now we can skip all this other stuff because we've seen a pattern, which is what a lot of math is about. We just do 4,000 times 1.04 to the fifth. And here we get 48.66.61. So again, I'm just highlighting here. These match up. So you made 866 bucks if you kept your investment in for 5 years. Not bad. But, I mean, let's say that you were a parent, a new parent, and you wanted to set up an education fund for your child. So let's say you wanted to drop $4,000 in and then leave it for 18 years, right? Until they go to university, and then they can start accessing that money. How much would it be after 18 years? Well, here we want to develop a formula. So to find the amount that your investment is worth, think about what we do. We take the principal that we invest, which we're going to call capital P. We multiply it by 1 plus the interest rate as a decimal, which the interest rate we'll call R. And then we raise it to the number of years that we're going to invest it for. So A is amount, P is principal, R is interest rate as a decimal, and n is the number of years that you're going to invest it for. This formula would also apply if you were taking out a loan. Okay? Because if you take out a loan from a financial institution, this time you're paying them interest. You have to pay them the cost of borrowing money. So like, let's say we decided we wanted to see what 18 looked like, 18 years in our example. So it would be 4,000 times 1 plus 0.04 raised to the 18. I don't have that off the top of my head. So it would be 1.04 raised to the 18th power, because you do the exponent first, times $4,000. And you get $8,103.27. So you would more than double your money. Okay? But a lot of times, if, like, say, you're a parent investing in your child's education starting from when they're born, you don't just put one amount of money in when they're born. Usually you contribute every year. So maybe you put 4,000 in, and then every year you contribute 1,000 to it. So it builds up even more. And then all of a sudden, when your child hits university, they have a nice little sum to pay for tuition and or boarding if they decide to go somewhere else. So the equation for this specific one, this is the general equation to calculate the amount of an investment after so many years at so much interest. But in ours, our equation would be the amount is equal to 4,000 times 1.04 to the n. That's what, in our specific example, that's what it would be. The one I wrote below is the general equation. Okay. So that's just sort of one example where we can use exponential functions. Okay. And it's a pretty relevant example because at some points in all of your lives, if you have not started already, you're going to be doing some investing.